What we're looking at here with our spoons is the idea of a curved mirror. If you take a look at your spoon, you'll notice that one side of your spoon, you can, scoop into a bowl of cereal or a soup, and the liquid will stay there, and you can slurp it out like a peasant. Or the back of it could be used for, playing spoons, right? If you look at the back of your spoon and you kind of pull one of these, you'll see that your reflection is upright. Like you see yourself in the mirror, just like if you were in the bathroom like we did previously. Like you just see yourself. So do that. Look at the spoon. Look at you. Look at you in the spoon. This looks weird whenever you're watching this video, but I'm looking at myself in a spoon right now, okay? If you turn the spoon to the other side though, you might notice that you've just flipped upside down. And that's really weird. So check this out. Right now, do you see how everything's upside down? Do you see how my microphone is down here and how my hand's upside down? This is my hand right here in front, but see how it's upside down in the mirror? Isn't that weird? But check this out. If I keep getting closer... What has happened? All of a sudden, everything flips right back up. And then it's upside down again. Something weird is going on here, okay? Something weird is happening with this mirror. See this? My hand's upside down, and then it's, oh, nope, now my hand's right side up. That's something really strange is happening with this mirror. And it's because this mirror is curved. So that's what we're going to take a look at here. We're going to look at some different cases on why spherically curved mirrors are causing these strange effects. And we're going to look at spherically curved mirrors for two reasons. One is that they are the simplest mirror mathematically to look at. Well, that's pretty much it. They're easier mathematically to look at. If we looked at a parabolic mirror, we could do more with it, but some of the issues with parabolic mirrors is that the math gets harder, but we would use them in the real life because they have less issues in terms of colors and focusing images. But for right now, what we're doing, spherical curved mirrors work very well. So let's dive into this. So the first mirror that we're going to take a look at is a concave mirror. And a concave mirror looks like this, okay? Where this is the mirror side and this is the back side of it, okay? So if this is a concave mirror right here, this is the mirror side, this is the back of it, okay? So that's your back, that's your front. And whenever we take a look at a concave mirror, we can create an image from our object using ray diagrams. And to use a ray diagram, we're going to follow three basic rules. We're first going to draw in the mirror itself. So you see here in the diagram, this is some mirror A right here, just like this. And we have an object, which we're always going to use an arrow as an object. And the reason why we use an arrow is because arrows have a top to them, where the arrow point actually is. And to draw a ray diagram for a concave mirror, we're going to draw a number of different rays here. We are going to start by drawing a ray that comes flat or horizontal off of the object, and it's going to strike the mirror. Now, we know that the angle of incidence has to equal the angle of reflection. And what's going to actually happen here is whenever this strikes the mirror, the normal line to this mirror right here is actually like this. So this arrow here, this ray, is actually going to reflect out just like that. And when this arrow reflects out just right, it's actually going to bounce out and pass through this point F right here. This point F is what we call the focal point. So our first ray comes out, hits the mirror, bounces, goes through the focal point, and then this light ray just keeps going on forever. Okay? So that's what we see initially for a concave mirror. Our next line we're going to draw takes us initially through the focal point. We're going to drive through the focal point, strike the mirror, and with the same argument as before, this line is actually going to come out flat. Okay, so before we went flat focal point, now we go focal point flat. We just like kind of do everything backwards. And we see when doing this that the two lines that we've drawn, one from up top and one from this one, are going to intersect at some point here. This point of intersection came from doing this at the top of the arrow, which means the top of the arrow is now down here. Well, if you were to draw lines for every other point of the arrow, you would eventually see that you would rebuild the arrow right like this. And this gives us the image. And this was our original object up here. Okay? So with just two rays, you can actually get an image off of a ray diagram for a concave mirror. Now there is one final ray you can draw. Personally, I'm really bad at drawing this last ray, so I don't bother with it. But one of the rays that you could draw is you could go looking at the top of the object. You could pass through what's known as the center of curvature right here. And we'll talk about exactly what that is momentarily in regards to the focal point. And if you pass through the center of curvature and strike the top of your object and you strike the mirror, this will give you a direct line back, and it will pass through the exact same point as the other lines did, giving you your image here. Okay? I'm really bad at drawing that one, and you'll see why just momentarily. So I don't like to do it. The line that I like to draw, if I'm not drawing lines 1 or 2, is if you actually have a ray hit this exact point here, it's like just hitting a plane mirror. And you'll get that, where the angle of incidence and reflection are the exact same. So I like drawing lines 1, 2, and then 3, well, I guess 4. I don't like this one up here. This line is, I'm always drawing it poorly. I don't really like it. But if you do, whatever floats your boat, okay? Now the reason why I don't like drawing that one has to do with the center of curvature and how it's defined. When we have a convex or concave spherical mirror, excuse me. Oh, that's a terrible line. Shing. This line going across here, this is the principal axis. It's the center line cutting our mirror in half right here. Okay. Now, if this is our focal point F, that focal point is defined as such that all light that is coming through and striking the mirror will reflect off the mirror and pass through the focal point. Okay? That focal point is a distance away from the mirror though. And the distance that this focal point is away from the mirror is little f. This is the focal length. Now if you're looking at this and saying, hey bots, the top of this is a shorter length than the bottom of this, yes, you're technically right. And this is why we don't use spherical mirrors. Spherical mirrors have like some issues associated with these distances being different. We are going to pretend, for sake of argument, that there is such a little curve to this that they're effectively the same top and bottom. Okay? But that is the focal length there. The center of curvature takes place twice the focal length away from the mirror. So if this is the focal length, if we go that same distance again, and you can't see this, but I'm literally holding my fingers up to my monitor to try to just match the distances the same. And here, let's bring in this camera. Like I'm literally doing this to see if I can draw it right. I'm going like this, and I'm going whoop, and my center of curvature should be right there. So when I draw this, that should be the center of curvature right there. Okay, so it's kind of a weird thing to draw. I always draw it poorly, and that's why I don't like using the line above this orange one right here, because I just always mess up that center of curvature. Okay, but the center of curvature is equal to twice the focal length in terms of distance. And the reason being is that this center of curvature, if we think about this mirror as being a sphere, the center of curvature, if you actually like continued the mirror all the way around, this would be the very center of the the sphere, which means that 2 times the focal point is actually equal to like the radius of the sphere itself if you were to continue that spherical mirror all the way around, which is kind of a weird thing to think about, but that's what's going on there. Now, if we take a look at something different, we'll be able to really use a little applet here to see just what's going on with these mirrors. Okay, so we're looking at array optic simulation, and this is something we found on GitHub. It's by Rick288, but if you start the application, you can actually go in and build array optic simulations. And what we have here on the left here, this is a spherical mirror, but it's not perfect. So we actually can use a ideal curved mirror, which exactly obeys the laws that we're gonna be looking at here, but it just shows it up like this. So this straight line here is actually a curved mirror, but it's drawn as a straight line, okay? Now what I have on the right here, this is a beam of light. So this beam of light is gonna hit the mirror and then bounce back. And we see this point right here. This point is the focal point. That point right there is the focal point. It's where every beam of light, as it comes in and hits this curved surface, bounces back and passes through that point. That is the focal point, okay, for a perfectly spherical mirror. So even if I, kind of like move this around, see how that focal point stays the same? That's because all the light that would be hitting this curved mirror is going to be passing through that focal point. And if we kind of move this curved mirror in front, we see the issue with true spherical mirrors. See how the focal point wants to be there, but as I shift it, it like kind of bleeds out in kind of weird ways. Truly spherical mirrors do this, but we want just the ideal case, which that focal point remains constant. It is exactly what we want. So that focal point is just where all the light is going to pass through no matter what. Okay, so we know that this is the focal point here, and instead of running in a beam of light, we're going to switch this to just a point of light, okay? So here is a point source of light. This is a light with, a bunch of rays. Here's just a few of them, but I'm going to make it have like nearly an infinite amount of rays, okay? So there's a bunch of rays that are coming out of this thing, and we see here, there's our focal point. Now, if I move this point source really far away, okay? Like a star would be. It's like an infinite distance away, right? That focal point is still right here. Look at this. The focal point is right there. Nothing's changed about that. And as I bring in our very distant light, look, it's like a tiny sun out here. See how that focal point doesn't really change? If our object is at an infinite distance away, all of the light is going to effectively pass through the focal point. But something weird is going to start happening. As we bring this in and in and in and in and in, notice how the focal point is starting to move. Do you see that? See how it's starting to move as I bring this in? As you bring this in, that focal point, well, the focus itself is the same, okay? That point right there, this is the focus. This is the focal point. But where all of the light intersects, that intersection is starting to move to the right. Where all of that light intersects, that is the image. The focal point is still back here. The focal point is still to the left. But the image has moved out. And as I bring this over and over, the image continues to move to the right. So the image is moving to the right. The focus is still back here. And when they overlap, we see that our object and our image are at the same location. Now, when I bring this inside, it's still moving to the right. So we see our image here. See how this is like a bright circle of light? It looks like a point source. As I bring this closer and closer, though, we're going to start to see something kind of weird happen. As I bring it closer and closer, notice that not only is the image getting farther away, but notice how at this point right here, it looks like I've just Hadouken! And I've just like, Kamehameha, like a line, a beam of light that goes out. And I can't really see where that intersection is. There's like, where's the intersection? The intersection is nowhere. What is going on? This is an interesting point right here. It turns out that at exactly this point, our object is at the focal point. And in just a second, when I bring this further in, we'll see that the light is starting to spread like that. So no image could be created. Well, let's take our rays of light and let's extend them behind the mirror. If we extend the rays behind the mirror, as we bring this in and we get to this point right here, the Kamehameha wave, notice how on the back side, when we move our rays behind the mirror, something has appeared here. And as we continue to move this closer and closer to the mirror, look, it's like we have an image. Except this image doesn't exist. This image is behind the mirror. It's all in darkness. All the light is on the right, but coming backwards, we see something. This is what you see when this occurs. Right now, you have an object far away from the mirror, and as you bring it in, you begin to see something virtually. You begin to see something behind the mirror here. Okay, there's nothing here, but that's where you think the object is. So you kind of get this weird effect. And this behind the mirror actually creates a virtual image for us, which is something that we've only briefly talked about, but that's what's going on. So there's actually 6 cases we have here for a concave mirror. We have it when the particle's at infinity, outside the center of curvature, at the center of curvature, inside the center of curvature, but before the focal point, at the focal point for the Kamehameha wave, and then when we go inside the focal point, we get this. So there's 1, 2, 3, 4, 5, 6 different things. And let's run it back to the notes so that we can see each and every one of them. So if we take a look at kind of drawing these, we'll see these 6 cases. One is at infinity, all the light comes in, bounces, and hits the focal point, and that's where the image is. For case 2, our object is outside the center, or it's within the center of curvature, but outside the focal point, and we see an image occur here. We see this image is upside down, just like you did in the spoon, and notice that this image is actually smaller than the object. They're different sizes. Woof. Sorry about that. I wasn't sharing my screen. So what we see here is that for our 6 cases, as the light's coming in from infinity, it's striking the mirror, and then it's attacking the focal point, and all the light hits that focal point. For case 2, we're outside the center of curvature, and that light goes in, we pass through the focal point, pass through the focal point and then bounce out, and we see an image. Notice that this image is flipped, and in this case, it is smaller. Okay? This flipped image means that it is real. It's a real image, just like the frog was. It actually can project. It actually exists. And this real image has to be flipped. That's the only way you're ever going to get a real image. They're always going to be flipped. When we're at the center of curvature, our object and image are the same size. It is flipped again, so it's flipped, meaning it's real. It has the same size. And then once we start getting inside the center of curvature, this is when we actually start creating a magnifying system. Our object is only this big, but our image is much bigger. It's still flipped, meaning that it's real, but we're bigger. And we're starting to shift the image out. When we reach the focal point, when we draw our lines, we see that, we take a line, we strike, and then we come through the focal point, and then you can't really draw the focal point line because you're at the focal point. You can't draw this line through the focal point here, you're at it. And that's where I like to draw the line where we bounce off the mirror and then come back out. Because when we do that, we find that these lines are parallel. And since these lines are parallel, they're never going to converge over here. These lines converge, these lines converge, these lines are parallel. And since they're parallel, they're not going to converge. But they're not going to diverge either. So we have no image. That's the Kamehameha wave. When you go inside that focal point, though, you see something really weird. And you have a very specific case that occurs for case 6. What first happens is when you try to draw your lines, you draw your line over and then you bounce it off the focal point. But you can't easily just draw the second line through the focal point and hit the mirror. That's not really possible. So it's easiest to once again just use this flat line, the plane, and bounce in and out. And when you do this, what you see is that these lines here, these lines are divergent. They're moving apart from one another. But what your eye is doing is it's backtracking them. Your eye is backtracking these lines, and your eye is pretending that the lines hit out here. There is no light here. This is just darkness. But if we backtrack these rays and they do converge over here, then our image is going to be upright, and it's actually going to be larger than the original object was. Because this image is upright, it is virtual. It actually doesn't exist. It's just our mind playing tricks on itself. It's a virtual image, and it is larger. Okay? So these are the 6 different cases that you could have with just a concave spherical mirror. Okay? And those are the 6 cases that you really need to be able to understand. You need to be able to pull them out of your pocket and kind of give quick sketches to them anytime you're asked to. So definitely study these up. Definitely check this image out. And if you've got access to my PDF that I have, make sure you're looking at that as well. But until next time, when we start looking at how we can look at the back side of the spoon, adios, and y'all take it easy.